Hi, I'm Nevin presenting gradient-based language model red teaming. The goal of this work is to find red teaming prompts which make the model give an unsafe response, as in this example. We use a classifier to measure if the response is unsafe. Red teaming data from humans can give us accurate and high-quality data. However, this process is very expensive. An example of this is the bot adversarial dialogue dataset. In this work, we focus on automated red teaming. Red teaming prompts can be used with RL from human feedback to improve alignment. When red teaming prompts are used as prompts in RLHF, the model will get a low reward on them, so it will learn to improve its output. If none of the prompts used in RLHF cause the model to say something unsafe, then the model will not be able to learn to improve based on the safety reward. Here are some related methods. Universal adversarial triggers finds prompts which produce a fixed response. Automatically auditing LLMs uses joint optimization to find red teaming prompts. In our method, we feed the prompt into the model and the model response into the safety classifier. The goal is to cause the safety classifier to label the response of the model as unsafe. We backpropagate from the output of the safety classifier through the model in order to update the prompt. We keep the model and the safety classifier frozen. One challenge is that the prompt and model output is discrete, so we can't backpropagate through them directly. Our solution is to use the gumball softmax trick. It works by adding gumball noise to the input and then taking the softmax. Given a probability distribution for each token in the vocab as input, we get an output similar to a one-hot encoding, where one token has a high value and the rest have a value of close to 0. The probability of each token being selected as the one with the highest value is proportional to the probabilities given as the input. This diagram shows the method in more detail. First, we run decoding given the prompt. Then we feed the result into the safety classifier to calculate the loss. This part shows how we feed the prompt into the model. The prompt contains 2 tokens and the response contains 3 tokens. X1 contains the probability for each entry in the vocab. Same with X2 for the second position. After the gumball softmax, we get X hat, which is similar to a one-hot encoding. We feed this into the model by multiplying the embedding of each vocab token by the corresponding weight. The gumball softmax is important because the model expects to receive a single embedding for each input instead of a mixture of multiple embeddings. After feeding the prompt into the model, we do decoding. This is identical to regular model decoding, except we use the gumball softmax in place of sampling from the output of the model. So the model predicts Y1, which is the probability distribution for the first token predicted. Then we take the gumball softmax and then feed this back into the model the same way that we fed the prompt into the model. This makes the entire decoding process differentiable. Next, we feed the prompt and response into the safety classifier. The classifier uses the prompt as context in order to evaluate the safety of the response, using this response token to separate the two. The safety classifier gives us a probability that the output of the model is safe. We use this as our loss because we want the output of the model to be unsafe. Given this loss, we backpropagate all the way into the input tokens. We initialize these input probabilities to the uniform distribution and then update them with multiple iterations of gradient descent. The safety classifier is trained to use the prompt as context in order to evaluate the safety of the response. However, this doesn't always work, and sometimes the prompt can trick the safety classifier into classifying the response as unsafe even though it isn't. The optimization process sometimes finds prompts like this. A simple solution is to not pass the prompt into the safety classifier, which we call response only. This avoids the problem but ignores cases where the response is only unsafe in context. The classifier still expects a prompt, so we pass in this hard-coded token in place of the prompt. The previous methods don't encourage the prompt tokens to be meaningful, so the prompts they find are usually gibberish. To mitigate this, we implement a realism loss, which encourages the prompt tokens to be similar to the tokens predicted by the language model. The language model predicts the distribution of the next token x prime given the previous tokens x. We use the divergence between x prime and x as an additional loss in our method. Another method to encourage realistic prompts is to start with a pre-trained model and fine-tune it to generate red teaming prompts. We pass in a hard-coded prompt to the pre-trained model. The method is the same as before, except we backpropagate into the weights of the pre-trained model to update it, instead of backpropagating directly into the prompt probabilities. We use an L2 loss to keep the weights of the model close to their original values. As a baseline, we use red teaming language models with language models. This work has the same goal as ours, but uses reinforcement learning to train a model in order to generate red teaming prompts. This method uses the output of the safety classifier as the reward in the reinforcement learning. We also use prompts from the bot adversarial dialogue dataset as a baseline. These prompts are generated by human raters to cause the language model to give an unsafe output. Once we optimize the prompt probabilities in our method, we greedily sample from them to obtain the tokens in a red teaming prompt. This means we pick the vocab token with the highest probability at each position. To generate a different red teaming prompt, we reinitialize the probabilities to the uniform distribution and run red teaming again. For methods which train a language model, like our fine-tuning method and the RO baseline, we train the model once, and then decode from the model with a temperature to obtain different prompts. We generate 200 prompts from each method for evaluation. We use greedy decoding to get a response from the model we are red teaming. Our metric is the fraction of unique successful red teaming prompts generated by each method. Successful means that the unsafe probability of the response as measured by a safety classifier is over 0.9. Our experiments use a lambda 2 billion parameter model with a prompt length of 6 and a response length of 4. We use a separate classifier for evaluation as we did for training to make sure that we're not just overfitting to the training classifier. X represents the prompt and Y represents the response, so the safety classifier here was only given the response as input in order to evaluate the safety. Our realism loss method does the best compared to all the other methods, and all of our methods do at least as well or better than the baselines. This safety classifier uses both the prompt and the response as input. Each method does best when it's evaluated with the safety classifier that was given the same inputs as for training. So most of the methods do better when they are evaluated with the safety classifier given both the prompt and the response. However, the response-only method does better when it's evaluated with the safety classifier given only the response. This column shows the results measured with the same classifier used during training. Most methods do better when measured with the training classifier, indicating that they are overfitting to the training classifier. We also measure safety using the toxicity classifier from the Perspective API to further verify our results. The results in this column generally line up with the results from the other safety classifiers. These metrics measure the prompts generated by the methods. PPL is perplexity of the language model given the prompt as input, so lower perplexity means that the prompt is more coherent. We can see that the realism loss method improves upon the perplexity, and the fine-tuning method improves upon it farther. However, the baselines have the most coherent prompts. As far as toxicity, the RL red teaming method produces the least toxic prompts. Out of our methods, the response-only prompts are the least toxic. We think that this is because in the other methods, the prompt can be optimized to be toxic in order to trick the safety classifier into thinking that the response is unsafe, so this steers it towards more toxic prompts. To demonstrate the strength of our technique, we run it on a model which is trained to be safe using data from humans. The results show that our gradient-based red teaming method is still able to find successful red teaming prompts, while the RL baseline and response-only method are not. With the RL red teaming method, it doesn't receive the gradient, and therefore it has a weaker signal to use in order to find successful red teaming prompts, so this could be why the method doesn't do as well as ours. One disadvantage of our method is that we have to fix the length of the prompt and the response in order to backpropagate. To partially address this, we run the method with different lengths of the prompt and the response. The original results have a prompt length of 6 and a response length of 4. We generally find that increasing the length of the response and the prompt makes the results better. This table shows the fraction of prompts and responses from each method which are in English and German. We chose those two languages because they appear the most frequently within our prompts. We experiment with a simple way to control the language of the prompts by filtering out the tokens corresponding to German words. The results for that is shown in these no German rows here and here. We can successfully control the language, but some of the tokens still slip through our filter. For the realism loss method, filtering out the German tokens actually improves the results, so we reported those metrics earlier. This experiment validates the usefulness of our red teaming prompts. We fine-tune a model to be less likely to respond unsafely to our red teaming prompts using direct preference optimization. Then we run the red teaming techniques again on the fine-tuned model. We find that training on these red teaming prompts makes the model much more robust to red teaming, as shown by the fine-tune on gradient-based red teaming approach here and here. The model fine-tuned on our prompts is much more difficult to red team. Our gradient-based red teaming technique was able to generate more successful red teaming prompts than the baseline using reinforcement learning. Having good coverage of model failure cases is important, so combining multiple red teaming prompts from different methods is useful. A risk of our work is that bad actors will use our technique to find a prompt which causes the language model to generate harmful content.